I'll be continuing on from where we were last week with a bit more complicated data analysis. So it's not as much content as last week, but it's more complex. So I'll be going through it, trying to go through it at a reasonable pace to make sure that we understand what I'm doing. So I will share you my screen and tell you a little bit about what I will be going through today. So hopefully this is sharing okay for everybody. I will just make it larger again. I remember the last time some people couldn't see. So just as a quick recap for people, last week we were looking at fitting of data. So what we did was put some straight lines through some data to try and get the slope of the line and the intercepts. We were also looking at some bad examples of some fitting. We were looking at fitting some simple curves. And then we went to a little bit more advanced case of using various functions to fit the data. And such as the sine or cosine function we see here, and the Gaussian and Lorentzian functions that we're looking at here. So these are just two different types of peak. And shown some error, how we can use the error bars to help us in the fitting by weighting the data points. And then we had some peak finding, some root finding to find where the function crosses over 0. And then we did some filtering of some data, so low pass filtering for noisy data like this, where we removed the high frequencies to get the green. Now this was all dealing with just simple data, all in one dimension. So what I'm going to do today is continue a little bit on with this one-dimensional data. What I mean is just some data plotted against time, for example, by talking about the what's the fast Fourier transform and how we can use it to look at periodic data. So, for example, like these sinusoidal data or audio, so music. And we can use it to analyze and filter this data. Then I'm going to move on to what was originally going to be the entirety of the second part of this course, which is looking at images and two-dimensional sets of data. So a lot of the work that I do personally in my research involves taking pictures with a camera and then extracting some useful information from the picture. And I will show you how we can do that with some example data that I have taken from our lab. And I'll also show some other techniques for working with images that may or may not be of use, depending on what area of work you're in. And hopefully, by going through this not too quickly, it can be understandable for you. So the first thing that I wanted to talk about is something called the fast Fourier transform. Now, I got the idea to talk about this section from one of my lectures when I was doing my undergraduate degree on signal processing and data analysis. And the entire course was on taking some measurement and getting useful information out of it. And one of my favorite examples was working with what's called the fast Fourier transform and the sound of a piano being played. So the fast Fourier transform is a computer algorithm that is part of the NumPy package. And what it does is it takes some set of data that's periodic. By periodic, I mean it has some oscillations like this. This is a periodic signal, and it converts it into a set of frequency data. By frequency data, what I mean is essentially relates to how often do these peaks in the data occur. So if you think about the case of music, if I have a tuning fork, I'm tuning my piano to make sure the notes are correct. I have a tuning fork at some specific frequency. Maybe it's 420 hertz, for example. And when I bang the tuning fork, it makes a single note. If I was to record that using a microphone, I would get a sound file. I could use the fast Fourier transform to convert this into frequency data, and I would see just a single peak at 420. If that doesn't make sense with my word description, hopefully by moving through the pictures, it will make sense. So as an example, I have produced, this data is already in the data folder for this lesson. Just to say, if you were here last week and you had the link to this data, it's the exact same file. So you can continue on from the same file that we're using last week. If you had missed it last week, you should have an email from Javid, which has the link to this Google Drive folder. So I have this piano chord.wav file, which is just the sound I made by playing a chord on a piano. I played 3 notes. And I saved it to my computer, and we can load that into Python quite easily by using this wav file function, which just is part of SciPy, which is a package we've seen quite a lot so far. And it loads the data in as 2 different types of information. The first being sample rate, which is essentially how many bits of data are there per second from the audio file. So if you've ever looked at music on your computer, you may sometimes see that it's listed as a sample rate of 44,000 or something. This is what this refers to. It means there are 44,000 bits of data per second for the file. And then the data itself. So this is essentially the volume or the amplitude of the sound file. And these 2 pieces of information are all you need to produce a sound on a speaker. So that's all that's saved in the data file here. And so if I run this section, we can see, like I said, we print out the sample rate, we get this number, 44,100. That is what we would expect. And then we've made, I just decided to plot what does this data look like against how long the sound file is. So the sound file is 2 seconds long. And we can confirm that by taking the length of the data, which is some number. I can actually print that to show you. So the data that's stored in this file, there are 81,000 data points, but we know that the sample rate is 44,100. So we can figure out how long the audio file is by dividing one by the other, just like this. Length of the data divided by the sample rate, and it gives us just over 2 seconds. So this is what it looks like. And if we were to imagine a speaker playing the sound, or your ears listening to the sound, the height of this is almost directly it's directly related to how far the speaker moves. So you can kind of think of it as a volume or an amplitude of the speaker vibrating. And so this up and down vibration is what gets transmitted to your speaker, which then turns into sound. But it may be a little bit hard to understand visually. So what we can do is actually play the sound. Now, as you can hear, hopefully that sound came through. it's a piano chord played on an electric keyboard, so it doesn't quite sound like a real piano. It's got a little bit of a computerized sound to it. And yeah, so that's how you can import audio into Python if you wish, and you can look at it. But as I mentioned, we want to use this thing called the fast Fourier transform. I haven't talked in detail about the algorithm because it's very it's quite a mathematical topic, and I don't want to spend too much time talking about the details of that. If you are interested, though, please do look at the link further up. But this is a very useful algorithm. It's used in many areas of research and in industry, technology, and especially in audio engineering and all of that sort of things. But it's one of the most efficient computer algorithms that exist. But we can use it very simply in NumPy by using the numpy.fft package. I think, sorry, I didn't show that earlier up here. Oh, I haven't shown it. Anyway, okay. So NumPy has this FFT package, which you can call like this, which has all the functions for the fast Fourier transform algorithm in it. And the simplest function is just called fast Fourier transform. And so it takes the data that we had, does a transform of it, and gives us back the frequency data. Now, I'm going to remove this line just to show you something. At first, it gives us something that looks like this. Now, this is, again, it doesn't look very useful. But what we actually have is this is the information about the frequency of the sounds. So this will have all the information about the notes played on the piano. But it's mirrored around the middle here. So we have exactly the same data again on the right-hand side, just in reverse. And that's a little bit annoying to deal with. So what we can do is use this function here called FFT shift, and it just shifts the second half of the data to the other side like this. And so it makes it so that you go up in frequency on one side and down in frequency on the other side. This is just it's just a side effect of how the computer algorithm works. There's nothing important in what's going on there, just to remember that it doesn't put the data in a normal order. So we use this FFT shift function. But it still looks a bit awkward to look at. We can't see a lot of detail. So what I'm going to do is just show you what it looks like up close. And so that's just taking half of the data here. So what this does is I'm indexing the array. This means every value of the array up until this point here, which is halfway along. Well, sorry, from, yeah. And what we can see now is that we just have, like I said, just this part of the data. We don't have this part over at the far end. I've had to do a little bit of calculating to figure out the frequency information here. So the Fourier transform doesn't understand anything about the frequencies. So we have to do that ourselves. All it can do is convert it into some kind of data, and we have to calculate the frequency. And that is just calculated like this. We calculate the time, again, like I showed you earlier. It's the length of the data divided by the sample rate. And that gives us something like 2 seconds. And then the frequency is just dividing this k, which is just an array of numbers that goes from 0 up into 81,000, the length of the data. And you just divide that by t. This, you can find information on where this comes from, if you wish, from the Wikipedia link that I showed earlier about the fast Fourier transform. But this is a simple way to calculate the frequencies that come out of the audio. And so now what we have, if we plot this, is the the frequencies of the sound in the file, and the amplitude of these frequencies, which is essentially how loud each of these frequencies are. You can think of it that way. But I want to just give you a close-up look to make it a bit more obvious what we're looking at. So this is the data that comes out. We have a lot of different peaks that show up, but we can start to work with. And so we know that I played a piano chord. So I just played 3 notes on the piano. So we should have 3 dominant frequencies. But also, when you play an instrument, you often also have overtones or harmonics, which are just multiples of the same frequency. This is on every instrument you'll ever play. When you sing, when you play the piano, you play the guitar, you can get these overtones as well. So that's why there are more than just 3 peaks. But you'll see this coming up in the next few sections, why I bring this up. So we can figure out the location of these peaks using this find peaks function I showed you last week. So here we're going to use the absolute value of this fast Fourier transform data. Oh, sorry. Okay, my apologies. I haven't explained one thing to you. One thing is what I showed you here. You see it has both positive and negative values, but the fast Fourier transform generates complex data. And what I mean by that is it generates numbers that are real and imaginary. If you're familiar with complex numbers, hopefully that makes sense. But we can't plot those on a graph. So what we do is we take the absolute value. So that just essentially says how big is the number, regardless of if it's a complex number or not. And so that just gives us purely positive numbers, and it gives us the height. And then we can do, like I showed you last week, we can set the height that we want. So I want peaks only higher than 60, so higher than, say, this point here. And distance of 20. This is just an arbitrary number I chose so that we don't get too many peaks close together. And then we can plot these all on the same graph. So of course we have our x-axis, which is the same in both cases, and we have these locations of the peaks, which I'm now plotting the individual points on top of the normal data like this. And so we get a bunch of different peaks like this. And then we can look at where these peaks are by just printing the numbers. And so we have a series of numbers here: 110, about approximately 110, 139, 165, 220, 220, 277, and so on. And if you're familiar with a bit of music theory, you may notice that these correspond to common notes in music. So the peak at 110 is the frequency of an A, so an A note. And then the 220 and the 440 are just multiples of that 110. So these are the overtones I mentioned before. So when you play a note with a frequency of 110 hertz on a piano, you also get the piano string also has a part of it that's vibrating at 220, and at 440 hertz. So you get all 3 of these, the bass fundamental note and the overtones present in your recording. We then see that we have one at 139, which is a C, and there's also one at 277, which is approximately double, and 417, which is again double again. And these 3 are now a C. And then the third ones we can see are 165, 330, which is here, and 497, which is three times. Sorry, I said double here, so this should be one time double and three times this one. Sorry, four times. And then this one here, 497, which corresponds to the E. And we can show the notes independently by just picking which of these correspond to what. So I've just said that an A was 0, 3, so this is 0, 3, which is this one, and 7, which is this one, which is the 110, 220, and 440. And I've done the same for C and E, just as we've shown. And then I plot them in different colors. And so we can identify which peaks correspond to which note that I've played on the piano. And now this is very nice because when I played this on the piano, I did in fact play the A, the C, and the E keys. So it's very nice that this has actually come up. So it's a good confirmation that this in fact works as we intend. So this is cool, but okay, now what can we do with this? Well, let's just say I was making some music. This is a very complicated way to do this. You wouldn't do this in real life. You would just play this piece again. But if I say I had made some music and I played the wrong note, and I thought, I only wanted to play an A, I only wanted to play the E key, but I accidentally hit the A and the C, and now my music has the wrong notes in it. So we can now, we can open this up in Python, and we can go in and try and delete the notes that we don't want. And so I have created we can create this list called delete. There are other ways to do this. This is just how I've decided to do it, which is the locations of all of the notes in the A. So, and that's the red crosses here, the 110, the 220, and the 440. And I've done the same with the C. And then what I want to do is just go through each of these peaks and just delete the data in here so that it doesn't exist anymore. And the way I'm going to do that is a little bit, how do I say? It's not very scientifically accurate, let me say, but it works. And that is just to take a little area, about, I've said 15, either side of the peak. So just take the peak, go a little bit to the left, a little bit to the right, and set all of that equal to 0. So that it just completely removes the peak. This number you can adjust on your own to try and make it as good as you like, because of course you do have these little bits either side of the peak. It's not a vertical line. It does have some shape to it. So the width of your area that you're deleting can be important. But then I do the exact same thing for C and just delete the same things for C. But then I can show you what that looks like by just doing the exact same plot again. And so now you see the areas that I've chosen, which are about 30 data points wide, or 30 frequency values wide, have just been set to equal to 0 down here. And I've marked where the peaks were originally to show that they are in fact gone. And now we just have this main peak for the E note and the 2 overtones here. That's interesting. So now we can try and see if that actually worked and play the sound back. Luckily for us, this exact same package we have in SciPy for the WAV files also allows us to save audio. So you could, if you wished, do all of your music production and editing in Python if you really wanted to. I probably wouldn't recommend it, but you can. But before we save the data, we have to convert it back from this frequency information back into this time series data I showed you before. And luckily for us, this this Python fast Fourier transform package has this function called IFFT, which just stands for inverse Fourier transform, inverse fast, Fourier transform. Inverse meaning to go backwards. So it just undoes the Fourier transform and gives us back time series data again. So we can have a look, and you see it looks sort of like an audio file. There's a little bit of something funny happening down here. This I am not sure how to overcome, but it seems to always be a problem. Because of this going backwards and forwards, you sometimes get little bits of data that appear where they're not supposed to be. So just ignore this part down here. But up at this part of the audio file, it looks similar to what we had before. It's got some large oscillation that dies down and then goes quiet. And I've saved this file as under a new name here. And we can, again, load that one back in and play it. And it might not be immediately obvious, but that now is just the E note. So if I play this one, and then play the original, it's not immediately obvious because the E is the loudest note in the chord, but you can hear there's a difference in the sound. The chord has more sound in there, like this. It sounds kind of louder, more full, whereas down here it just sounds like a single note. You may hear there's a funny thing happening at the end of the audio file because of this here. It starts to replay almost like a mirror image of this. But so this was an assignment question that I had during my bachelor's degree that I thought was really interesting application to for this algorithm because it's something that I would have never considered you could do in Python. I never would have expected you could edit sound like this. So I wanted to just, again, link back to what we talked about previously with this filtering of the data. So there's another way we can instead filter the data. So if you remember last week, I can actually show you, we did this low pass filter here of this data, and we used this so-called Butterworth filter, which looks something like this. So we had some cutoff frequency after which we didn't want that any data of that frequency or above to show up in our measurement, and so we filtered all of these high frequency spikes out of the data to get this green curve. Well, we can do the exact same thing with audio. So we can, again, generate a filter the exact same way. We have this low pass filter function. It's the exact same function as last week. And the application of the filter here. But now we can just change the cutoff frequency to something a bit more relevant to the audio frequencies. For this example, I've chosen 220, which is the first overtone of the A note. And we can just say, I want everything higher than 220 hertz to be filtered out of the audio. And so we can create this filter by, again, this is the exact same as last week. I think I have more detail on what we're doing. Up there, we generate some frequency axis down here using this freq_z function. And we generate a filter using this butter low pass function, which is included in which is using this function here, which is part of SciPy. This butter is part of SciPy. And we can see now we have something that looks exactly the same shape as last week, where we now have this cutoff at 220 hertz. So this should hopefully attenuate anything or cut out anything higher frequency than 220 hertz from our audio file. Just to make it more visually clear what is happening, I want to plot this on the same frequency axis that we saw from before for the audio frequencies. And you can think about this red curve as the filter. Up here at high part of the filter, everything underneath this curve will pass through. And as this drops off, all of these peaks out here will be either significantly reduced in height or removed entirely if they're out here. And so we can kind of look at this and we can see, okay, the cutoff is about 220, which is here. And so that lines up nicely. And so we should just end up with a collection of low frequency notes once we apply this filter. So we can apply the filter to the data. Sorry, okay, this line should be moved. That's a little bit confusing for my explanation. My apologies. We can apply the filter to the data using this function, which I defined earlier, by putting in the data, the cutoff frequency, the sample rate, and then plot the new filtered data. So that's this Y. So again, I'm just using the fast Fourier transform to show the frequency information. In this case, different to what we did last time, we apply the filter directly to the audio data. So we don't need to Fourier transform it first before applying the filter. I'm just using the Fourier transform to show you the effect it has. But we can see here very nicely now that these peaks do not go larger than the filter. And they have now been successfully kind of cut out from this. And so this is the sort of filter that you would often use again in audio recordings. Low pass filters are good for cutting out kind of high frequency background noise and so on. But we can also use them, just to change what we're listening to. Again, we can use this wavefile.write to write this as a new file using this. I should explain how this works. When we write this, you just pass in the sample rate and the data that you have. But you have to make sure you convert the data to a float. This was something that I had originally forgotten. This is just purely because this function only takes data of this type. So this is just this just converts the data from one type of data, which is a float 64-bit floating point number, to a 32-bit floating point number. There's no real difference in what we're concerned between these two numbers, but it's just a difference in the way that the numbers are stored on the computer. But then we can play this, and you can hear now that it is a low frequency sounding note. It's only the lower frequency tones that are present, and all the high frequency sounds have vanished, which is exactly what we'd expect from a low pass filter. Now, what I would like, well, hopefully if that was understandable, my idea was to provide a small sort of assignment question to do in your own time, which is following the exact same steps I have outlined above. Do the same process that I did to delete certain notes on a different audio file. So I've provided a second piano chord. This one is the same. It's an A. I played an A chord, but I added an extra note that shouldn't be part of the A chord. And what I would like is if you can try and follow my steps that I did exact before to identify which is the note that is unwanted in the piano chord and delete it and resave it. And if you can do that, then I think that's be an interesting task. And hopefully there's enough information in my example up above for you to follow along with that. So I've given you kind of a section. You can write some code in the file directly here and just work from there on. Great. Okay, so that was just a small part that I had still left over from the last lesson. And so now I'd like to move into kind of the next part, which is working with images in Python. Now, working with images in Python is useful because a lot of times when we're analyzing data, well, at least in a lot of areas, such as in my case in physics, we take pictures with a camera quite often of our experiments, but also people who do biology or use a microscope to look at well, anything small, looking at cells or bacteria, people who are working in engineering or in kind of making microscopic structures or all sorts of areas of research. Images are a very easy way to capture a lot of data because you have whatever you're trying to measure. You just take a picture with a camera and then you can look at it later. And luckily for us, Python is very nice and very easy to work with images in. There are a variety of packages that allow us to use to import to work with images. So one of those is PIL, which I think stands for Pillow, I believe, which is an image library or Python image library. And that's one that I'll be talking about today. There is a few others, such as OpenCV, which I believe German will be talking to you about in the next 2 weeks in his part of the course, which is another way of working with images. And then I'm sure there are many more packages that can do this as well. But today we will just be focusing on using PIL to load in some images and then working with them using NumPy, because that's the simplest way to do so. So we can take any image. In this case, I have an image. Again, it's one I showed at the start of the course. It's just a picture of my cat. And we can load this into Python very easily by using this, this Python image library function just called image. We go and we can just go image.open and give a file name, and then it loads the image for us. And then we can plot it using the matplotlibs, which is the Python plotting library. If you remember, we have matplotlib.pyplot like this. This has this function imshow, which just shows any two-dimensional set of data as an image. I don't remember if I showed you this last week, but what I can show you as an example is I can make an array that is, say, 30 by 30. And then I can set kind of like this. Oops. Nope. What I'm doing is setting everything from 20 to 40 in both directions. I'm going to set that equal to 1, so that should make a square. So now I just have a two-dimensional array that's 0 everywhere except for a square in the middle, which is 1s. And then it can show that as an image. Oh, sorry. Okay. Never mind. My mistake. Sorry, I made the array the wrong size. There we go. Now, so we just have an array that's 60 by 60. I made the middle area 1s, and you can show the array as, and it shows it as an image. So any set of two-dimensional data that has columns and rows, you can show that as an image, which in itself is very useful for visualizing what you have. Even if your data isn't from a camera, it's not a photo you've taken, or it's not normally something you'd look at as an image, it can sometimes be very useful just to have a look and say, what does my data look like if I use ImShow? And you can gain some good insight into what you're doing that way. So I'd recommend doing that if you have some two-dimensional data. But moving on, we can use any image just as we would a normal Python data structure by such as indexing it like this. So if I take this region of 150 to 250 in the rows, and then 70 to 160 in the columns, and then have a look at the subset, I can get the eye of my cat, for example. And you can do this to anything. You can take regions of the data and manipulate it as you would with any other set of Python data. Now, because this is a photo, right? It was taken from my phone camera. The data actually stores 3 separate channels, which are the colors of the image, right? So we take a picture, we have this RGB data, or the red, green, and blue channels, and it saves each of these as part of the array, as a separate 2D array, and then it stacks them all together to make the image. So if I can show you what I mean. Oops. I've shown the shape of it. So you see that the full image is 434 by 512, which is the shape of the photo. But there's also another dimension, which is the third dimension, which is 3. And so each of this 3 indicates the 3 different colors of the image here. And so you can, of course, look at individual channels of the image if you wish. So this here is the way of indexing it to do that. So the colon here just means every value in this dimension, every value in this dimension, and the first, I guess you'd say the first color channel, in this case, the 0th color channel. And I can plot that. I'm going to use the red color map just to indicate that this is the red channel. And so you can see that it still has image data in there, but there are kind of details of the image missing. So, but you could do that with any other channel as well. What you can do is also manipulate the different color channels, such as deleting, in this case, delete the green one. So that way we'd only have an image that is composed of red and blue. So I'm going to copy the image just so that we don't edit the original file, so we can use it later if we need to. And then I'm just going to take the same thing as before, take everything in the next color channel, which is the middle one in this case. So if you remember, we indexed 0, 1, and 2 for red, green, and blue. And I'm going to set all of that to 0. So just completely wipe out the green channel, and then plot the image as normal. and you see now it's got a purple tinge to it. And that's because if you have just red and blue channels, then the resulting color is going to range from red to blue, and so in between will be purple. And so you end up with this kind of purpley image. I could do the same thing and delete the blue channel, for example, and end up with something yellow and orange, or I can delete the red channel and get something kind of between green and blue. So you can work with these images however you wish, just like normal Python data structures, which is very nice, because it means you don't have to learn anything new when working with images if you understand how to work with data normally. You can also make your images grayscale if you wish. This is not really useful for data analysis, but I just wanted to demonstrate. Sorry, this was my mistake. This was my mistake from when I was editing the file. And you can just turn it into a grayscale image. This isn't of any real use in the scientific sense, but it's just showing you can manipulate images as much as you like while from any sort of photo if you wish. But techniques that we will want to use when working with data is how to filter an image. So by filtering, I mean it in the same way as we saw last week or even earlier today, which is removing unwanted noise or parts of the signal that we don't like. So the simplest way that we often will filter an image is using to remove some noise is using a thing called a Gaussian blur, or a Gaussian filter. And this can help reduce noise in an image by blending pixels of the image together. An example of a noisy image would be if you have your camera and it's low light situation, so it's quite dark. You may recall that if you use your phone camera at nighttime, it's often the images are quite grainy. They're low quality. There's lots of pixelation of the data. This sort of situation is where you could, if you wanted to, apply a Gaussian filter to help kind of clean up some of this noise. But rather than working with some experimental data here just yet, I'm going to again use the same image of my cat because it's a good test photo, and I'm just going to make it a bit noisy. And so what I've done to do that is just like I did last week when I was creating fake data to fit. I just used this NumPy random.normal function, and this creates random numbers with a normal distribution. So that's sampling from a normal distribution or a Gaussian distribution. That's the same shape as the image, and that gives a big 2D array of numbers between kind of 0 and 1. Then what I'm doing is multiplying that by the square root of the image. Now this is a technical thing, because oftentimes when you are working with a scientific camera, you have noise in your image equal to the square root of the image. Now this comes from some statistics called Poisson statistics, which is to do with counting. And so I've just put it in here as an example. I think if you, I'll make a note here that the noise is added based on Poisson statistics. So this is just a I guess a common way of understanding the uncertainty or the noise in counting data or image data where you have pixels with numbers in you. But I think, yeah, if you would like to know the details of that, I suggest reading more on this. The Wikipedia page will be perfectly fine for that as well. But the main thing that we care about is that this just generates some noise that's proportional to the image in that sense. It's just, so what it means is it just takes all the pixels of the image and it makes them it jitters them around a little bit. So you can see that now the image still looks exactly like we had before, but you can start to see the noise. You can see the red, the green, and the blue kind of spots showing up. And this is because the different color channels now are noisy, and so they don't add up to the color that the image should. And so this could be something that you're working with in your experiment if you're trying to have an image and you have all this noisy, speckly stuff on your image that you don't really want to deal with. So that's where we can use this Gaussian filter. And luckily for us, again, SciPy has a function for it. So you may be starting to notice that SciPy has functions for almost everything useful. SciPy and NumPy are incredibly powerful, and if you ever are struggling how to do something, it's worth having a look at SciPy or NumPy to see if they have actually already done it for you. It can save a lot of effort. So they have this ND image, which just means n-dimensional image. I think is what that is what that means. N meaning just a number, so some multi-dimensional images. And we can just use this Gaussian filter function straight from there. You just feed in our image, which is noisy image in this case. And then we give a sigma. So this, if you remember the Gaussian function, maybe I will show you what I mean just to make it easier. The Gaussian function looks like this, right? And so the sigma is the width of the function, so the width between across here. And so what the width is important in this case because what it's doing is saying how many, the width in pixels is how many pixels should we include in the averaging process. And then I tell it the axes I want, which is 0 and 1, which means vertical and horizontal, because this is a multi-color image. I don't want it to average the color. Then it just turns out gray. So now the way this function works is it makes a little Gaussian. So like this curve that I showed you before, with a width of 2 pixels, and then it moves around the image, covering every pixel and kind of averaging all of them in the region of the Gaussian. And so that if you make this sigma bigger, it averages over a larger range, and if you make it smaller, it averages over a smaller range. So you can think about this as well as being the larger the number, the blurrier the image gets, the more it blurs the image. The smaller the number, the less it blurs the image. I'll show you this in a second. But so we run this through, and you see we get the result out, which it is blurry. It's not as high quality as before. We've lost some of the finer details of the image, such as the whiskers up the top or the little furs. But you see that the color, the speckliness of the color, the random red and green dots and blue dots have been pretty well taken care of. And the effect of this sigma, if I'll show you, if I make that, so this makes the Gaussian bigger, so it averages over a larger range. You see now we get a very blurry image, but you see the colors now are very good. So the bigger you make sigma, the more you can clean up your noise. So the image is not noisy anymore. You see the colors are really good. But of course, we've lost all of the detail of the image. So it is a bit of a trade-off, or you have to make a decision. What do I care about more? Removing the noise or keeping the sharp details? And sometimes it's not, sometimes you can't always have an optimal situation. You just have to go with the best result you can get. So in say my case, for example, we'll often have data that we have to filter, and you will lose some fine detail, but you can still get the important information you need, even though it is now blurry. And so you can see here, right, there's some kind of trade-off. You can get a little bit of the finer details of the shape, but there's still a little bit of, you can see the pixelation of the colors. It's not, hopefully you can see that on your screens. Yeah, so you have a kind of trade-off between the detail and the filtering. So I didn't show this with experimental data primarily because I thought this sort of image has interesting features. It's a multi-color image, so those are interesting to analyze, but also it's got the fine details, the spiky bits, and also some good range of colors that shows off how this filter works effectively. I can show you later on how it looks applied to experimental data. But first, this is where I think I'll spend quite a bit of time explaining this next section. So this is now how to use actual experimental images and obtain something useful from them. So rather than just filtering some photos like we've been doing, this is now taking actual data that we have taken in our lab here in Japan and make a measurement from the data. And so I'm going to go through this quite slowly because there's a bit of information here. Because this is experimental data, I don't want it to be too complicated. So I've included all the data again for you, so please feel free to have a look. It's in the Google Drive folder under this. There's a folder with this name, and it's a series of data files which are saved in a FITS format. So actually, I can hopefully. Oh no, I can't show you that because I'm sharing the tab differently. Okay, but in FITS format, FITS, and so this is an image format you can read about here. I believe it was originally put forward by NASA, so the American Space Agency. As it's an image format commonly used by astronomers around the world, but also it also has its use in many other areas because it's a useful way to take a picture. And the reason for that is, one, it stores data in a binary format. And by binary format, I mean it just stores numbers per pixel. So it stores just an array of numbers that go from 0 to some large number in the shape of your image. That's very nice. There's no complicated image what's the word, formatting. So like if you use a bitmap, a BMP image, or a PNG image, like for example, or a JPEG, right? These all have different levels of image compression. They have complicated encoding of the data that the computer understands to open it in a photo format. If we want to take scientific data, we don't want data that's has some complicated encoding. We don't want data that's had compression. We want the original data taken from the camera. And so that's why the FITS format is very nice for this. There is, of course, other ways to save raw data, but this has a lot of features. that we like. One of which being that you can store text information inside the image as well, inside the header. So you can store information about what the photo is inside the photo in a thing called the header, and then you can store your data in the data thing. I'll show you this in a bit. All the files we'll be using for this section have a simple naming scheme. They are called, the files in this folder have the name PGC underscore a number followed by the letters MS, which just tells you the time the photo was taken in milliseconds after some point of our measurement. So the files are labeled PGC underscore 1 MS underscore 2 MS and so on. And then there's another number after that. It goes after the MS. It also has another underscore and then another number going from 1 to 10. And that's just because we took each of these images 10 times at the same point. So we just did the measurement 10 different times and saved them all with a different name. Again, I'll show you shortly this in the code so that it makes more sense. Now, the overall goal of this section is to take all of these photos, load them into Python, and then calculate the temperature of a cloud. So we have a gas cloud on the camera, which is some kind of cloud of atoms that we have. And we want to measure the temperature of that. The way that we'll measure the temperature is by how far they move in a certain amount of time. So we're looking at the velocity or the speed of the atoms. How fast are they traveling? Then once we know how fast they're traveling, we can figure out their temperature very easily with this expression here, where there's just some constant times the temperature is equal to the essentially equal to the kinetic energy, which is just how heavy the atoms are times their speed squared. So it's quite a simple expression. So let's start moving through, and hopefully it'll become clear how all of this applies to the figures as we go. So importing these FITS images can be done with this AstroPy package, which is another astronomy package. So I previously told you about Pi Astronomy. There's also this other one called AstroPy. They both are quite similar in many ways. But it has this this FITS function here. Oops. Under astropy.io.fits. So this IO just stands for input and output, which is just opening and loading and saving files, and the FITS files. We're also going to be using this package called glob, which is a funny named package. But what it does is lets us locate files in a directory on our computer. So if you're ever working with real life data and you need to load in lots of files, it can be very tedious to manually type in all the file names. So what we can do is use glob to find all the files in a directory that meet a certain criteria, and then it brings them into Python. So as an example, we've moved our Python directory inside this folder for these images. And now I can just go use glob like this to find every single file in this folder that has the extension of .fits. So and then if we print that out, we see that it's now given us this big array full of all of these different file names. So this is the file name format I was telling you about before. PGC underscore 1 ms, which is 1 millisecond, underscore 7, it's the 7th image, .fits. But you can notice that the images are not sorted in any sensible order, right? They're in a seemingly random order. So we want to sort these files. because these are, like I mentioned, these are taken in order of time. So we want to put all of the images in time order so we can figure out how fast things are moving. So we want to get the times that all of these pictures were taken at. Because we've saved them into the file name, we can just use the file name to get the times. So I have this line, which looks long and complicated, but what it's doing is it takes for x in files. So that just means it takes for every element inside this list of files. It just takes one at a time. So that's a string. So say this first one, pgc underscore 1ms underscore 4 dot fits. And then it says it splits the string into multiple parts. So the split command takes an argument, such in this case it's an underscore, and it looks for the underscores in the string. So this one here and this one here, and then splits it into multiple pieces based on those underscores. As a simple example, I've said, for example, the word banana. If I was to split it based on the letter N, it would return this list here. So BA, A, and A, because it's taken the N as the splitting point and split it either side. Then it's taken this N and split it either side. So when working with file names, this split function is very useful. And in this case, I've taken the number 1 element because, as you can see, it returns it as an array. So we have to index it based on what part of the string we want. Because if I look at the naming convention here, the 0 part of the array will say PGC, the 1 part of the array will say 1ms, and the 2 part will say 9. So by taking part 1, I get the part that is the timing, or the number followed by the ms. I can then split that again, like this. By splitting it by ms, it just pulls the number off the front and then gives us the number back. So now it just goes through each of the files, breaks it down into to locate this number here for each of the files. It then checks if I've already done it by saying if the file has not already been loaded, then add that number to this list that I've called times. So it's a rather complicated way, essentially, of saying go through all of the files and pull out the timing numbers and put them into a list. So what you'd get at the end is some list that goes from 1 to 10 in this case, or 1 to 12 in this case. Again, this doesn't sort the times. They're in a random order because the way that it, okay, not random order, but it's not in a time sorted order. So we can use this NumPy function called sort, which sorts it from lowest to highest. And so that then, if we run this, we now see that the numbers go from 1 to 12. So that if you were to look at the files, you'd see that the numbers go all the way up to, well, 12. They're not in order, so it's hard for me to show, but it goes from 1 to 12. The reason I've done this is just so that now I know at what times do all of these pictures take place. And so now we can actually go through and open all of these files and plot them in order to see what it looks like. But I think it's probably worth me explaining a little bit more what these fits images are, because it's not something that I imagine any of you will have come across before. I hadn't come across it until I started doing this work, so I think it's not something that you'll normally come across outside of, potentially outside of astronomy. It doesn't really come up much at all, I think. So I'm going to just open one of these files and show you what it looks like. So we can just load it using this, again, this fits that I showed you before that we've imported. You just go dot open and give it the file name, and it gives you a file. But if we print this file, it is some unusual object. It's not something that we're familiar with in Python. It doesn't look like an array of numbers or a list of information. It's some complicated looking object. But it's not that hard to understand in reality. It's just like a container or a box, and inside that box are two things. One of which is the data that we care about of the image. That's the photo that we've taken. And the other one is the header. The header is just a collection of text information about the picture. And you can usually put whatever information you want into the header. Certain cameras that save in this format by default will automatically put information into the header. Most of the time, we don't ever care about the header. We just want this data. And so, yeah. The other thing is that this object here is called an HDU object. Don't worry too much about that. But the key thing is that you can have as many of these HDU objects per file as you like. This is another reason why this is a nice image format, is you can have multiple images saved in one file. So if you take lots of photos in quick succession, you can save them all into the same file, for example. But these images I'm showing you here only have one photo per file, so we just have to make sure we take the zero element of the file, because you can see that it's an array. The 0th element being this, and then you just go dot data to pull the data out. You can also go dot header to get the header information. And then we can also plot the image data as well. Now, if I show you the data, you see it's just an array of numbers, so it's nothing useful. The header, however, you can see here, the header is a whole bunch of words, right? It's just a whole bunch of words and some dashes. It's just a bunch of information about the image. So it's just printed in a very inconvenient way. So that's what I mean by storing text information in the header. But we never need to worry about this. We never need to use it. But by taking the data like this, we can then use this imshow function that we've been using to show a picture. And this is what it looks like, the photo taken on our camera. Now, this might be hard to understand, so I'll try and explain what we're looking at. The bright region in the middle here is a cloud, or a gas cloud of some atoms. So in our case, it's rubidium. The type doesn't matter, but it's just it's a cloud that we've taken a picture of, and we've shine some light onto the cloud, so it lights up. Take a picture, and we get the cloud. And this is what we want to be analyzing: is this cloud is going to spread out, and as it spreads out, we can measure how fast it's moving. How fast is it spreading out? And that will tell us how hot this cloud is, the temperature of the cloud. So this is just one image, but we have, if you look in the folder, you'll see that we have 12 different time steps and 10 different images. So we have approximately 120 images to go through. So we don't want to go through them one at a time. That will take too long. So we want to do a loop and go through all of them automatically. So here I'm going to be using this function called enumerate. This is just a nice way to loop through more than one variable at the same time. So you're likely familiar with a for loop, right? If I just have a simple for loop like this, it loops through each of the elements in this range, so 0 to 10, and then it just prints it out one at a time. So 0, 1, 2, 3, 4, and 5, and so on. So this is obviously a simple concept in programming, but this is still a for loop, but instead of just looping through one thing, we can, Python lets us do this this nice thing called enumerate, which lets us just loop over both two things at the same time. So I can say for I, comma, jj in enumerate like this, and print them, and you see it just each time it goes through, they both just go up by one. The reason that this is nice is because I can do something like this. I believe the syntax is correct. No. I believe this. Oops. Nope. Sorry. Anyway, I won't go into that. I'll spend too much time debugging my own code. But you can essentially have different ranges here as long as they're the same length, and so you can just step through multiple different numbers at the same time. So the reason I want to do that is because I want to step through each of the time values, so the 1 to 12 milliseconds, and also this additional. I just want to loop over it some other number of times as well. So I use this this enumerate to do that, and then I open each file with a particular time, and save the data into an array, and then average them at the end. Now this is the reason this is a little bit of a more complicated one to loading in each of the data. So I've built an empty array. This is an array that is empty. There's nothing in it. And then I'm going to use the append function to just add an element to the end of the array. I don't know if you've come across this before, but if I have some array that looks like this, it's empty, and then I go my array dot append, oops, 1 like this, and then I print the array, right? It just adds the 1 in there. And so you can just append data as much as you like. And so then you can also, append another number on the end of it. Oops, sorry. You can just append again and again and keep adding things to your array. So I want to add the first time image, which is PGC underscore. In this case, it is for the first time we go through the loop, right? This is 1 because it comes from times. 1 ms underscore 1 makes the full file name. I want to append that data to my array. But I have 10 images of the same thing that we want to add all the images together. The reason we want to do this is because it helps remove, it's another way of doing reduction of noise in the image, is by adding a whole load of the same image together and then averaging them, you can remove fluctuations on the images. And so then I go through the rest of the images with the same file name, but with a different final number from 2 up to 10 in this case, and just add them all on top of the first one. So I realize this might have been a confusing way to explain this. So now I have 10 images that have just been added together. So that means every pixel of each image has just been all added together. So I just have so now I have one final image that is the sum of 10 images. And then I just divide it by 10 because it's the average or the mean of the image. This is one common thing when working with uh, noisy data like this. When you do an experiment lots and lots and lots and lots of times, you want it to be reproducible. One way to deal with the noise is to average multiple of the same images of the same thing together. So that's what we're doing here. The result of this is that we just have 12 final images. So we've turned 120 images into 12. Is the main result of this loop here, which I will run. I'll show you what these images look like in a second. But before, actually, let me show you what these images look like now. No, sorry, I'll show you a bit later on. Sorry about that. So we're working with camera data, right? And we're trying to figure out velocity or speed. And to figure out speed, we need to know distances. You know, if you want to know how fast something is going, you have to know how far it's traveled in a certain time. So it's, you know, like the speed of your car, for example. If you're driving, you know, it's just a distance per time, kilometers per hour or meters per second or so on. It's just how far does something go in a certain amount of time. So to figure out distances here, we have some conversion based on the camera. I'm just going to tell you what this is in this case, but you can always find this for most cameras. For our camera, we know that each pixel of our photo is 4 micrometers, which is 4 millionths of a meter, so a very small distance. So essentially, the total imaging area of the whole camera is 4 millimeters across and 4 millimeters down. And then it's 1,000 by 1,000 pixels. So each pixel is about 4 micrometers. And so we just make some arrays. So just an array which I've called x1 and x2. This is just something that gives us the distances across and down on the image, which we'll need to figure out speed. And I've just used this NumPy linspace function here to do that. It's a little bit messy, but it's just making sure that it goes from, it just takes the length of the whole image, which is 1,000, as we can see here, it's 1,002 or 1,004, depending on the axis, divides it by 2, and then just goes from minus that number to plus that number. So that just means if it's 1,002, for example, it goes from minus 501 to 501. It just means that the middle of the image is 0. So it's just a useful way to do that. We do the same thing for both dimensions. So it goes from minus 501 to 501 on one axis, and then the other axis is minus 502 to 502. And then we multiply by 4 micrometers. And then we now have something that is distance away from the center of the image. So it's a useful thing when you're working with these sorts of things, is always figuring out how can you convert your photo into real life units of measurement. Distance is what you'll always get from a camera. Essentially, it's hard to measure anything else, but distance is a easy thing to get from a picture. So now this next part, so all of the stuff I've just talked about is probably a little bit complicated or confusing, but hopefully it's understandable. But now that we've done all of this, we're going to do exactly what we did in the first week. Well, sorry, the last week's session. If you remember, we used this Gaussian fitting function. That was this nice kind of nonlinear peak. So this is an example of where this Gaussian fitting function is useful. Because if you have a gas, the shape of a kind of a gas cloud, if you have it confined and you let it go, the shape of this gas cloud will be some kind of Gaussian distribution, so that it'll look like a Gaussian if you take a picture of it. And this is just the nature of hot gases or hot fluids as well. So any kind of thermodynamics type situation. But that's some physics detail that is not super important right now. We want to just define a region of the image. So as I showed you, you can index an image, right? You can just take a subset of the image, a smaller region of the image to make things easier. Like I took the cat's eye earlier and just made a small picture of it. I'm going to do the same thing for the image here by just defining some region that I want to take of the image based on kind of a starting point and end point. And then like this. So I just take I've just drawn a square on the image to show the region that I'm taking. So it goes from 200 to 600 along the horizontal axis here. 200 and then has a length of 600, and then it goes from 80 down to another 600 later. Well, the square is showing a bit of a funny size, but essentially that's what we're doing. Is just taking a smaller region, because this information out here is useless to us. It doesn't tell us anything about this bright cloud. It doesn't give us any information about how it's traveling. Then what I've done here, this is just an extra little line I should mention, is I've taken the time. If you remember, the time numbers are the milliseconds, so 1,000th of a second. And I've divided them by 1,000. So the way I've written that is exactly the same as dividing by 1,000. To convert the 1, 2, and 3 into millisecond numbers, and that's just because it makes it better for calculations. Okay, so now what we want to do is go through every single one of these images and do like we did last week and look at, so we're going to look at the data across, say, this direction or this direction, and we're going to see some shape of the cloud based on the height of the, based on the brightness of the pixels here, and we're going to fit a Gaussian to it. And because we're doing that with 12 images, it's nice to look at every single one of these images and at the same time and see if it's actually working as we intend. And so that's where this there's a nice function of matplotlib called subplot. The subplots function lets you make just a grid of images. You can make it as big or as small as you like. Like this here. So I can just create a figure, which I've called fig2, and it's got some axes, which are the horizontal or the axis lines associated with it, by going plt.subplots 4, 3. And now what that does is it makes a grid of images that is 4 images across and 3 images down. So it just makes a grid. And so you can make this as whatever shape you like. It just makes a nice regularly spaced grid of pictures. And by then using this function ravel on the axis, it turns because this axis thing is this is an array that tells you which figure you're talking about. So if I have a 4x3 grid, this is an array that represents the locations of each of these figures. But by using this ravel function on it, it turns it into just a long list, and so I can just index them in order. It's purely for convenience. You don't have to do this part. So if I didn't do the, let me just do something to demonstrate what I mean. I think I can do this. Oh, maybe not. Okay, but so this is what the subplots will look like. It's a grid of figures. Don't worry about the overlapping numbers. That's you can spend a very long time formatting these to look nice. For now, you don't need to worry. And so normally when you want to index these, right, this is the top left corner. This would be 0, 0, because it's the 0 in the vertical, 0 in the horizontal direction. And so you go 0, 0, 0, 1, 0, 2 down here, 0, 3 down here. But to make it easier, what this ravel does is it just turns it into a 1D array. So it'd be 0, 1, 2, 3, then 4, 5, 6, 7, and so on. It's purely a convenience function. You don't need to use it. So this is just what we're going to do to look at each of these images in one go. So actually what I will do before we move on, just to make sure that it's understood, I'm just going to go like this. Uh, okay, never mind. Sorry about that. Never mind that. I don't want to spend too much time mucking around with that. It's always hard to write Python live in front of people. It's very easy to make mistakes. So now what this does. Oh, yes. Sorry, I saw a hand raised. Do you have a question? Okay, maybe. Okay, I see the hand's gone. Okay. So what we're going to do is just go through each of the images one by one, and turn them into something that we can fit with a Gaussian. The way that we'll turn them into them is just this function called sum. We just take the image, and essentially, if you think of an image and you just flatten it completely, you squash the image, so now it's just a one-dimensional array using sum by adding up every row or every column to make a one-dimensional thing, and then we'll plot it. So that will give us essentially if we look as though we were looking side on at the camera image, right? So it's I don't know how else to explain that, but that will then give us something that's the shape of approximately a Gaussian, and then we can use our fitting function that I introduced last week again, this SciPy curve fit, to fit the Gaussian function to the data. And if you remember, you need some x data with the horizontal axis of your fitting, which in our case is our camera pixels, right? It's this data that tells you the distances. The data that we're trying to fit, which is this image data that I've summed up to make one-dimensional, and some initial guesses of the parameters. If you remember, you have to provide you should provide some initial guess for what you think the fitting function parameters should be to help SciPy fit it. Depending on the complexity of the function you're using, you can sometimes avoid it, but for anything slightly more complicated than a straight line, maybe, you should always give some initial guess parameters. The best way to create these guess parameters is just to plot your data on a figure and have a look and try and read off the plot these parameters. So in this case, the amplitude of the Gaussian function, you just look at how high is the peak. For the position, of the function, it's where does the center of it sit. For the width, it's how wide is the function. For the offset, it's how high off the bottom is it sitting. So I'll plot it soon and I'll show you. But we get these parameters, these we're guessing what we think it is, and then SciPy can use that to better fit the data. And that, of course, returns us with the optimal fit parameters. So the best fitted versions of these parameters that we guessed, and this covariance matrix. If you remember from last week, I briefly talked about the covariance matrix. It's the main thing we care about is the diagonal part of the covariance matrix is this related to the standard deviation of the data. So it just helps us understand how good we fit the data. And then I just go through every single file and add the fitted position of the width of the fit. So remember I said we're trying to calculate the velocity. We want to know how far things have traveled in a certain amount of time. And so what happens when we let this cloud move over time is it gets bigger and bigger and bigger, so the width gets larger and larger. So by saving the width of the cloud, we can determine how far it has traveled, how far the atoms have traveled in some time. And then I've done the same thing, but for the other dimensions. We have the horizontal axis of the image and the vertical axis of the image. We can do it in both dimensions just to check. I just did the same thing again, and then we just plot the fitted parameters over the top. And so that gives us something that looks like this. So each of these images as you go along is of 1 millisecond later in time. So this is the first one, then the second, third, fourth, and so on. And you can see the blue curve underneath is the data, and the yellow is the fit of the Gaussian. So this is just like I showed you last week, where you can just fit very nicely the data shown. It doesn't matter that it starts to go off the frame here. You can see that it doesn't quite fit the full function, but it doesn't matter because you can see it still gives a nice fit. The next set of data down here is just, like I said, I did one in the vertical direction, which is these top images, and one in the horizontal direction, which is these bottom images. I can tell which is which because this has a big spike here, which if I show you the image, right, we have this vertical line that runs through the image. Now, I haven't talked about what this line is, but it's not important right now. It's just part of our experiment. But this vertical line here shows up as a bright spike. So that's how we can tell which axis is which. But you can see that it fits very nicely, the shape of a Gaussian. It's and if you might be able to tell by eye, it's a little bit hard, but you can see that every image, it gets wider, right? The first image is a little bit narrower, and then it gets wider at the end. Hard to tell necessarily by eye going through each one by one, but the increasing in the width is related to the velocity of the atoms. How fast are they moving as the cloud kind of spreads out over time? So I mentioned that we saved all of the width of the cloud as this parameter called fit1 in the loop. That was this part here, where I'm appending the number 2 element, which is the width of the cloud, to this thing called fit1. It's got this series of numbers here, which is the width. These widths are in the units of these are actually, it's all in meters. So this is a width in meters. So it's very small, very small. We're looking down here at the end here. We're only looking at almost 2 millimeters across. So it's a very small cloud. But so yeah, then how we can calculate the temperature. Now, if you remember, I showed you this expression at the start. Let me go to the very beginning. This thing here, I have the temperature of something is related to its velocity or its speed, how fast they're moving, squared, times the mass, how heavy the object is, and then in this case divided by this constant. Now this constant is just related to how gases, so like air, for example, or oxygen, nitrogen, whatever you have. If you have a gas, this is just related to how gases behave when they're warmed up. So we can get the velocity because, like I said, we know how far we've got distances traveled, how wide is the cloud after a certain time. We know how long it's taken to spread out because all of our files are named after times, so we can get a velocity, right? By distance. Distances divided by times gives you velocity. We know the mass, we know how heavy the particles of the gas are, and this is a constant number. It's known. So we have all the information we need now to get the temperature. And the way we want to, the easiest way for us to do that actually is just to plot the data by taking the time squared and the width squared. Now, let me just make a note of why we do this. So remember, we have something that looks like temperature. Temperature is equal to m, which is the mass, times the velocity squared, divided by some number k. If you remember from last week, this is a straight line equation, right? We fitted straight lines last week. This is a straight line where we have v squared, v squared, the velocity squared, is the x data of our straight line. So it's the y, the x data of our straight line. Sorry, this is the y data, I should say. I made a mistake. Yeah, and so we can essentially organize this in such a way that we have v squared on the y-axis and time squared on the x-axis, because we have that velocity is sigma over t, which is the width over time, the width of the Gaussian over time is the velocity, just because it's distance divided by time. And so we plot that as a straight line in yellow and in blue from the other dimension. Don't worry about that one. I'll comment it out for now because it's just complicates my explanation. Oops, sorry, wrong one. So the tricky thing about demonstrating stuff in real time is it's very easy to make mistakes. And so here we have along the horizontal axis here we have the times in millisecond, time that we had before, milliseconds squared, because we've done time squared. And in the vertical case we have the width squared. And so then we can fit that with a straight line. With just this polyfit function. Again, I showed you this last week. We put in some x horizontal data, some y data, tell it it's a order 1 polynomial, which is a straight line, and it returns a straight line equation for us. And that straight line equation has a gradient, which is this p of 0, because p is the return parameters, and it has an offset, which is p of 1, which is a y intercept. And we can just plot that on here, which is the yellow line, and we can see that it's a very nice straight line fit. Now, as I said, we were looking at, I'm going to rearrange this to make it a little bit, just to bring it back to how it was at the start of the lesson. We're looking at this expression, right? I told you we're trying to find the temperature. What we've essentially done here is rearranged this equation so that we're showing, we've essentially split the velocity into distance and time and plot them against each other, such that the gradient of this equation is now the temperature. So this sorry, the gradient of this equation is related to the temperature. So the way we've rearranged that is we have, sorry, let me just rewrite this down. So we have sigma squared equals it should be KB K underscore B times the time divided by the mass. So I've just kind of taken the no, sorry, that's not. Ignore that. Sorry, I've just made this to avoid making it confusing. Essentially, the important thing here is that the gradient of this line is related to the temperature through this equation. And so the gradient is this P of 0, and so we just multiply it by the mass, divide it by KB, and we get the temperature. Oh, there seems to have been a mistake done with my units conversion somewhere. I did check it earlier today, but the answer should actually be 25 microkelvin. In this case, the units of temperature are in Kelvin or microkelvin. If you're unfamiliar with the Kelvin scale, it's the same as Celsius, but offset from 0. So if your temperature in Celsius is minus 273 degrees Celsius, right? That's as cold as you can go. In Kelvin, that is 0. So 0 Kelvin is as cold as you can go. And this is should be just a little bit above 0 Kelvin. So this is very, very, very cold. This is almost as cold as is physically possible to get something. So that is an example of taking some experimental data and analyzing it to obtain a usable quantity. I spent quite a long time going through this section because I really wanted to try and make sure that I wasn't confusing with what I was talking about. So hopefully it was understandable. Looking at the time, I don't think I will have time to go through my last two sections, but please take a look. They are a little bit more simple than what I've gone through, the last two little bits. They're not too long. Please take a look at those if you wish. That's about fitting a two-dimensional image. This is a little bit more complicated. I won't go through it, but it's instead of converting it into a one-dimensional thing, you can fit directly on the 2D. But it's a little bit about why that's probably not a good idea. And then finally, I bring back the Fourier transform that I talked about for the audio file, and I show how you can use the Fourier transform on any set of data, not just audio. So I show you with an image how you can take a picture and do Fourier transforms of a picture to also filter images that way as well. But I think I should leave it there, and just in case people have some questions, and I can have some time to answer them. So yeah, thank you very much for your attention.
Thank you very much, Dr. Dylan, for the nice and great presentation. It was super. If there is any question from the participants, please feel free. Yes, sure. We will upload the video as soon as we can.
Mm-hmm. And yeah, you're more than welcome to share this one as well.
Yeah, we will do it.
Great. I noticed there was a question earlier on that I didn't have the chance to answer. Sorry, from rz.y about any specific way to select the best data fitting algorithm for a data set. That is a very good question, and unfortunately, there's no magic way or no automatic way to know what the best fitting algorithm is for a data set. At least not one that I have ever been made aware of. If you're, for example, fitting something with a straight line, so like this data I've just showed you here, usually you'll find the different fitting algorithms. So if you use SciPy or NumPy or other fitting algorithms, they'll usually give you very similar results. And oftentimes you can try different ones and see which gives the best result. When it comes to more complicated data fitting, so fitting like the Gaussian fitting here, for example, I don't have any real answer for that. It's oftentimes, at least the way that I approach it and that people that I work with approach it, is to just use what we think is going to be best and see what the result is. And so there is a lot of trial and error when it comes to complicated data fitting. It's you oftentimes have to just try something, see what it looks like, and then go back and make changes based on what the result looks like. So if your fitting algorithm isn't working, you can try changing the algorithm. If the function you think you should fit with, so say I tried this with a Gaussian, it looks like it fits nicely, but if it didn't fit nicely, I would just have to go and change what I fit with. And that is something that I recently did experience in my work, is that we had to completely change how we were analyzing data because the function and the algorithm that we had been using for about 2 years, we realized actually wasn't working very well. So we had to change it. And it's, yeah, I have to say, I think, unfortunately, I don't think there's a simple way or a specific way to select the best algorithm. I think it's a lot of it is just based on experience, your personal experience, and what seems to work well. So hopefully that's answered your question.